locomotive killed American steam, not because of how it looked, not because of marketing, not because of regulation, but because of what was inside it. The Locomotive F-unit and its 567 series diesel engine did something between 1939 and 1960 that no American steam locomotive could match. It worked, predictably, reliably, cheaply, 24 hours a day. The car body is iconic. The 567 prime mover is more important. This is what is actually inside the locomotive that ended the steam era, and why every modern American diesel-electric still owes its existence to it. In 1939, American railroading ran on steam. Tens of thousands of steam locomotives operated across the country. Every Class I railroad had massive shop facilities, staffed by hundreds of workers dedicated to maintaining the steam fleet. When the Electromotive Corporation introduced the F-unit in 1939, the response from established locomotive manufacturers was skeptical. The F-unit was lighter than a comparable steam locomotive. It was smaller. It carried less fuel. It seemed, by every conventional measure, like a step backwards. But the F-unit had something no steam locomotive could match: a power plant that could run continuously, restart instantly, operate at any throttle position without thermal stress, and be maintained by mechanics rather than by entire shop facilities. What was under the F-unit's hood was the most consequential piece of mechanical engineering in 20th century American railroading: the 567 prime mover, the engine that killed steam. The Electromotive 567 was a 16-cylinder, two-stroke, V-type diesel engine. The number 567 referred to the cubic inch displacement of each individual cylinder. 16 cylinders multiplied by 567 cubic inches gave the engine a total displacement of just over 9,000 cubic inches. The two-stroke design was the critical engineering choice. Most diesel engines built before the 567, and most diesel engines built since, used four-stroke combustion cycles: intake, compression, power, exhaust. The 567 used a two-stroke cycle, compression and power happening in every revolution rather than every other revolution. The result was that the 567 produced power on every single rotation of the crankshaft. A four-stroke engine of comparable displacement would produce roughly half the power output. The 567 punched far above its weight class. But a two-stroke diesel has a fundamental problem. With no intake stroke to draw in fresh air, the engine cannot breathe naturally. The 567 solved this with a roots blower, a positive displacement supercharger driven directly off the crankshaft that forced compressed air into the cylinders during the brief overlap between exhaust and combustion. The roots blower scavenged the cylinder, flushing exhaust gases out through ports while simultaneously charging the cylinder with fresh air. The valve at the top of the cylinder controlled exhaust flow. The intake was through ports cut into the cylinder wall that the piston exposed at the bottom of its stroke. This combination, two-stroke cycle, roots blower scavenging, cylinder wall intake ports, gave the 567 its distinctive sound: the deep, continuous idle, the instant throttle response, the sharp acceleration, the unmistakable roots blower whine. Anyone who has ever heard an EMD diesel idle at a crossing has heard the 567 architecture at work. Fuel delivery was equally important. The 567 used unit injectors, individual injection pumps mounted directly on each cylinder, rather than a central injection pump distributing fuel through hydraulic lines. Each cylinder had its own metering, timing, and atomization. The system was mechanically simple, electrically straightforward, and dramatically more reliable than the central injection systems used by competitors. And the cylinders themselves were designed for individual replacement. A 567-cylinder assembly, the liner, the head, the valve gear, could be removed and replaced as a single modular unit without disturbing the rest of the engine. Maintenance that would have required tearing down a competitor's prime mover could be completed on the 567 in a single shift. But the 567 was only half the story. What that engine fed into was what actually made the F-unit kill steam. The F-unit was not really a diesel locomotive. It was an electric locomotive that carried its own power plant. The 567 prime mover spun a generator. The generator produced direct current electricity. The electricity fed traction motors mounted on the axles. The traction motors turned the wheels. The main generator was mechanically coupled directly to the prime mover crankshaft. There was no transmission. There was no gearbox. The 567 spun the generator continuously, and the generator's output was modulated by exciting or de-exciting its field windings, essentially controlling electrical output rather than mechanical input. Each powered axle carried a single traction motor mounted alongside the axle inside the truck. The motor drove the axle through a single reduction gear set. The arrangement was mechanically simple, electrically rugged, and gave the F-unit one of its defining performance characteristics. A steam locomotive's tractive effort drops off as wheel speed increases. The faster the wheels turn, the less force they can apply. A direct current traction motor does the opposite. Maximum torque is available at 0 revolutions per minute. As speed increases, torque tapers gradually but remains substantial across the entire operating range. This meant an F-unit could start a heavy train from a dead stop with full power applied immediately. A steam locomotive of equivalent rated horsepower would slip its drivers, struggle to gain traction, and require careful throttle modulation to avoid losing the train. The F-unit just pulled. And because the F-unit used electrical control rather than mechanical control, multiple F-units could be coupled together and operated from a single cab. The lead unit's engineer controlled the throttle, the brakes, and the dynamic braking of every coupled unit simultaneously through a single 27-pin electrical jumper between locomotives. 3 or 4 F-units could be coupled together. The total horsepower scaled directly with the number of units. The total crew did not. One engineer and one fireman could control 12,000 horsepower of locomotive, power that would have required 4 crews on 4 separate steam locomotives. The F-unit also pioneered dynamic braking on a large scale. By reversing the function of the traction motors, using them as generators driven by the train's momentum rather than as motors driving the wheels, the F-unit could slow itself electrically without applying friction brakes. The energy generated was dumped to resistor grids on the roof. The mechanical wear on brake shoes dropped by orders of magnitude. Everything about the F-unit was easier than steam, and easier was what killed steam. A typical American steam locomotive was available for revenue service about 60 to 70% of the time. The rest was maintenance, inspection, water and fuel servicing, ash removal, and the constant labor required to keep a steam plant operational. An F-unit was available about 90% of the time. The 567 prime mover needed scheduled maintenance every 12 to 18 months for major work. Daily servicing was minimal: fuel, lubrication, brief mechanical inspection. The locomotive could run continuously for thousands of miles between service stops. A major Class I railroad steam shop facility employed hundreds of workers: boilermakers, machinists, hostlers, ash pit crews, water plant operators, coaling tower operators, sandhouse workers. The infrastructure to support a steam fleet was massive. An F-unit fleet required a fraction of that infrastructure. A diesel maintenance facility employed dozens, not hundreds. There was no boiler to maintain, no firebox to repair, no ash to remove, no coal to handle, no water to treat. The operating cost difference was decisive. F-units cost roughly 50% less per locomotive mile to operate than equivalent steam locomotives. The fuel was cheaper, the maintenance was cheaper, the crew requirements were lower, the infrastructure was smaller. Once American railroads understood the math, the transition happened with brutal speed. The Norfolk and Western dieselized in 1958. The Union Pacific kept some steam into the early 1960s, but operated diesel fleets that vastly exceeded their remaining steam roster. By 1960, mainline steam in America was effectively dead. The F-unit and its 567 prime mover were not the only diesel locomotives sold during this transition. ALCO built diesels, Baldwin built diesels, Fairbanks Morse built diesels. But the F-unit was the dominant product, and the 567 was the dominant prime mover. EMD's market share routinely exceeded 70% during the dieselization era. Over 7,000 F-units were built between 1939 and 1960. They served every major American railroad. They hauled freight, passenger, and mixed traffic. They worked main lines, branch lines, and switching service. They were the most successful single locomotive design in American railroad history. And the 567 prime mover that powered them was so successful that EMD continued building it with refinements into the 1960s. The successor 645 series engine was a direct evolution of the 567. The 710 series engine that powers most modern EMD diesels descends from the same architecture. The F-unit itself was retired from mainline service across most American railroads by the late 1970s. The streamlined cab unit format had been replaced by hood-style locomotives that were easier to maintain and offered better crew visibility. But the engineering inside the F-unit did not retire with the locomotive. The 567 prime mover continued in production into the 1960s. The 645 prime mover that replaced it was a refined 567. The 710 prime mover used in modern EMD locomotives is a direct descendant of the same architecture. The most successful modern American freight locomotives, the SD40-2, the GP38-2, the SD70 series, all use prime movers whose lineage traces directly to the 567, the two-stroke architecture, the roots blower scavenging, the unit injectors, the modular cylinder construction. Every defining feature of the 567 survives in some form in the locomotives operating American railroads today. A small number of F-units survive in preservation. Several are operational. They are most often seen leading excursion trains for railroads that want to celebrate their dieselization era. The locomotives are charming to look at. The 567 prime movers inside them are still doing the work they were designed to do 8 decades ago. The 567 prime mover was not the most powerful diesel engine ever built. It was not the most thermally efficient. It was not the most technologically advanced. It was simply the most appropriate engineering for the application. Modular, durable, maintainable, and produced in numbers that allowed it to dominate an entire industry through sheer ubiquity. American steam locomotion ended because the F-unit's 567 prime mover made it economically impossible to continue, not by being more powerful, not by being more impressive, by being mechanically simpler, operationally easier, and economically lethal to every competing technology. The F-unit is famous for its appearance. The 567 prime mover is the reason the F-unit matters. Everything else about the locomotive, the warbonnet livery, the streamlined nose, the porthole windows, is decoration on top of the most consequential diesel engine in railroad history. The EMD F-unit and its 567 prime mover changed American railroading more thoroughly than any single locomotive design before or since. It was not the largest. It was not the most powerful. It was not the most beautiful. It was simply the locomotive that made every other approach obsolete. This is part 3 of our What's Under the Hood series. Part 1 covered the Union Pacific Big Boy and its articulated steam drivetrain. Part 2 covered the Pennsylvania Railroad GG1 and its electric power architecture. Both are linked in the description. Part 4 will cover the Pennsylvania Railroad K4 Pacific. The locomotive that proves engineering excellence does not require engineering extremity. Conventional steam mechanically optimized through restraint rather than ambition. Subscribe so you do not miss it. There is more about American railroad engineering than any single video can deliver. Each of these locomotives deserves a full mechanical study. We are working through them one at a time.